Welcome to The Explainer. Today we're diving into the quest for absolute certainty in a world that is, well, fundamentally uncertain. We're going to get inside the mind of the surveyor, the engineer, the builder, the people who have to construct our reality with millimeter precision.
I mean, really think about that for a second. You've got two teams, hundreds of meters apart, digging through solid rock. How in the world do you make sure they don't miss each other? Not by a meter, not even by a centimeter. This isn't just some thought experiment, it's a real-world problem with incredibly high stakes.
So to solve a problem like that tunnel, we first have to wrap our heads around this fascinating paradox that's right at the heart of all modern engineering. We need perfect precision to build, well, everything. But we live in a world where perfection is basically impossible.
This is like the first rule of surveying. It's the absolute, unshakable truth. No matter how fancy your laser is, how advanced your GPS, every single time you measure something, a tiny little seed of uncertainty, an error gets planted. A surveyor's job isn't to get rid of it, because that's impossible. Their job is to understand it, to manage it, and ultimately to conquer it.
Okay, so to manage that error, you first have to know your enemy. Surveyors are in this constant battle against what you could call a fog of uncertainty, and it's created by a few different types of errors. Let's meet the villains of our story.
First up, you've got your systematic errors. Think of these as the predictable bad guys. It's kind of like a watch that's always 5 seconds fast, A GPS satellite's clock might be a tiny bit off, or its orbit isn't exactly where we think it is, and its signal gets delayed as it punches through our atmosphere. But here's the good news. Because they're predictable, we can actually model them and correct for them with math. But then there's the other enemy. And this one is way harder to deal with. Random errors. This is just chaos. It's a GPS signal bouncing off a nearby building before it hits your receiver. It's tiny little variations in the antenna itself. It's just the inherent fuzziness of any observation. You can't model this stuff perfectly. It's just statistical noise. And this is where the real challenge begins. So if every single measurement is flawed, how do we build anything at all? Well, we fight back. And our weapon is math. Surveyors have this whole arsenal of statistical tools to slice right through that fog of uncertainty and find what is most likely the truth. Okay, check this out. Here's a classic surveyor's dilemma. We need to find the exact coordinates of this point P. So, we measure it from a known point using route A. That's the long one, 4 kilometers, and we get one answer. Then, we measure it again from a different route, route B, which is shorter, only 2.5 kilometers. And we get a different answer. So, which one's right? Well, the honest answer is probably neither of them is perfectly right. But what we can do is find the most probable answer. And we do that with a cool tool called a weighted average. You can think of it like putting together a council of experts. You listen to what everybody has to say, but you give more importance, more weight, to the opinion of the expert you trust the most. And this just shows you the logic so perfectly. Step 1. You assess your data. In surveying, a shorter measurement usually means less error can creep in, so route B is considered more reliable. Step 2. You assign more mathematical weight to the coordinates you got from route B. And then step 3, you run the calculation, and boom, it pulls the final answer closer to B's measurement. We haven't guessed. We've used pure logic to find the single most trustworthy location for point P. Okay, so how does this kind of statistical thinking play out in the real world? Let's take it out of the textbook and apply it back to that high-stakes challenge we started with, that tunnel. The engineers have their target. Over a distance of 210 meters, the two ends of this tunnel have to align with an error of less than 3 centimeters. Let that sink in. 3 centimeters. That is an insanely tiny target. If they're off by more than that, you're talking massive delays and huge costs. So here's the real question. To hit a 3-centimeter target from 210 meters away, what's your margin for error? How much can your initial direction be off by? Go on, take a guess. A degree? Maybe a tenth of a degree? The answer is 29 arc seconds. Now, let me put that into perspective for you, because it's pretty mind-blowing. An arc second is 1/3,600th of a single degree. That means your aim can't even be off by 1/100th of a degree. It's a level of precision that is almost impossible to even imagine, and you can only get there by mastering this whole world of error. But here's where the surveyor's quest for certainty takes this really surprising turn. Sometimes, the most powerful tool in your kit isn't about finding the answer. It's about recognizing that an answer, with the data you have, simply cannot be found. All right, take a look at this geometry problem from a real civil engineering exam.
We've got this shape, a quadrilateral, and we've measured 6 of the angles inside it. The goal is to calculate the last 2 missing angles, theta 1 and theta 2. Seems pretty straightforward, right? You've got a bunch of data.
Wrong. The official answer key to this problem is just stunning. It simply says, cannot be solved. No matter how you twist the equations, there is no single, unique mathematical solution.
So why? What's going on? Well, it's because even though we have a lot of data, we don't have enough independent information to isolate our 2 unknown angles. All the known angles are related to each other in a way that creates this kind of mathematical loop. To find theta 1, you need to know theta 2, and to find theta 2, you need to know theta 1. You're just stuck.
And this right here is the ultimate lesson from the surveyor's world. The goal isn't just to crunch numbers and get an answer. It's to understand the limits of your own information. True mastery isn't about forcing a solution. It's about having the wisdom to recognize when the data itself is telling you that a single, certain truth is simply out of reach.
Which kind of leaves us with one last big thought. You know, we navigate our world with GPS coordinates that feel so precise, so absolute. But as we've just seen, every single location is really just a most probable value that's floating in this sea of uncertainty. So if every single point has a margin of error, does any place or anything truly have one perfect singular location? It's something to think about.